All right, welcome back. Happy Wednesday. So I just handed back the tests. If you have individual questions about your tests, see me individually right after class, for example. I have written the mean and the median up here. I think the results of this test were pretty darn good, so nice job. And now we're moving on to a new topic today. There we go. Anybody else not get their test back? Okay. All right, so looking at our calendar, a new topic for today is approximating definite integrals. This will be a breath of fresh air for those of you who are tired of finding antiderivatives. We're not doing any of that today. We will do more antiderivatives this semester, but we won't have any new antiderivative rules. We're done learning techniques of antidifferentiation, but today we're just going to do approximation stuff. So a welcome change, perhaps. Here in the calendar, it says your grading choice is due. Now, that was assuming I gave you the test back last class, which I didn't. So that grading choice is going to be due next class, so this coming Friday. I will pass around this sheet on Friday, and you're just going to find your name and either circle one of my prescribed grading options, or you're going to make your own personalized thing. I'm going to walk around today just to show you what it looks like, but this is part of your homework for Friday's class, is to just think carefully about how you want me to grade you at the end of the semester. You're committing to this on Friday, okay? All right, also coming up on Friday, I will hand out project number 4 on Friday, but right now there's no project outstanding for you guys. Any questions on the calendar? Okay, so here we are at the top of page 9, our daily summary. This semester we have learned many techniques for handling different types of integrals, but the fact of the matter is we still can't integrate most functions. If you just make a function up, the odds are we won't be able to find an antiderivative of it. If you just make something up, it's not hard to make one that's impossible to antidifferentiate. Thus, our techniques for approximating areas by using right rectangles, left rectangles, or midpoint rectangles, we've seen all of those, are pretty important. And there are some other shapes that we can use that will get us even better approximations, and we study them in this section. So in the demo number 1, we're going to let left parentheses n and right parentheses n denote the Riemann sums. Remember where we would use right rectangles or left rectangles to approximate the area under some curvy thing. We're just getting notation for n being the number of rectangles that we use. And so each of these guys is going to represent an approximation of an area. Okay, so let's take a look at a specific example. We're going to approximate the integral from 1 to 3 of 3x squared. It's quite silly to approximate this because we can find an antiderivative of 3x squared pretty darn easily. So we will to compare our approximations to the exact answer, but most of the time the function is too complicated to do an antidifferentiation on. We're going to find left of 2 and right of 2. So let's see if we could do that down here. We're going to shade in the rectangles down below. So let's look at the first picture on the far left here. We're going to find left of 2, which means 2 what? 2 rectangles, that's all the 2 means. So we're going to do 2 rectangles here. The integral is between 1 and 3. So looking between 1 and 3, if you needed to cut that into 2 equal pieces, how long is each piece? Is 1 long. I'm going to do the calculation here, even though it's so easy in this case, but how come it's 1? It's because you're subtracting and you're saying, oh, there's a difference of 2 altogether, and you are cutting it into the 2 pieces that we are asked for. All right, so that's the calculation, of course, is equal to 1 in this problem. Okay, so that means that our points of interest are 1, 2, and 3. And if we're doing left rectangles in this first interval between 1 and 2, which point determines the height of the rectangle? Is 1, the point on the left. So you go from the point on the left up to the curve. That is the height of your rectangle. From here, we're going to draw to the right until we are directly above the 2 and then go straight down. So that is the first left rectangle. Go ahead and draw the second left rectangle. And again, between 2 and 3, you pick the left point to determine the height. So hopefully your picture jives with mine. Same idea for the picture on the right-hand side. Let's use 2 right rectangles. So for example, between 1 and 2, which endpoint determines the height now? 2. So you go to 2, up to the curve, that's the height. And now which way am I drawing? to the left because we were going between 1 and 2. So there's your first right rectangle. And then between 2 and 3, we'll use 3. So those are our two right rectangles. Clearly the left rectangles, will they be an over or underestimate of the true area under the curve? Definitely an underestimate. Right rectangles will be an overestimate, right? Pretty bad overestimate, but that's okay. All right, but now we actually want to find the values here. So left of 2 really means find the total area of those two left rectangles. So let's do it. Left of 2, let's see. So area of a rectangle is base times height. The base is 1 in this case, times the height. What's the height? It's 3. Should we be able to look at the picture and look across and say, oh, it's about 3, or is there a more accurate way? Yeah, we plug it in, right? I mean, you know you're on the function 3x squared, so if you plug 1 in for x, 3 times 1 squared, that's the height. That's the exact way to do it. That's the way we should be doing it. So the area of that first green rectangle is 3 times 1, or just 3, plus 1 times, and now what number are we plugging into the function? 2. F of 2 is 3 times 2 squared, which is 12. So 3 plus 12 is 15. That is what we mean by left of 2. Questions on that? Can you guys take about 60 seconds and find right of 2 right now? And check in with each other, make sure we're all doing the same thing. Okay, so 1 times 12 plus 1 times 27. Is that all right? Okay, so then the true answer, the true value of this thing is definitely between 15 and 39, for sure. It's someplace in between. Okay, all right, let's move on to maybe a better way, more accurate way to approximate the areas up above is number 3. We're going to approximate that same thing by using n equals 2 trapezoids. We're going to draw 2 trapezoids in this picture on the left, and we're going to find what we call trap of 2. So that just means use trapezoids, 2 of them. So again, going between 1 and 3. So I'm going to highlight the same points, which is 1, 2, and 3. Those were the important ones. And now we're going to draw trapezoids. So it's a little bit different here. Go ahead and from each of these 3 numbers, draw a vertical line up to the curve. Good question. We will try that right after we do our trapezoids. Okay, and then to complete the trapezoids, all you're going to do is connect the dots. You've got 3 dots on this curve, and so it's going to be kind of hard to see. I'm sort of going to exaggerate so we can really see, but if you connect those first 2 dots at 1 and 2, it's definitely a little above the curve, right? Fact is, it's not all that much above the curve, so it's even hard to see, which indicates that this is going to be a far better approximation than either of the rectangle ones that we did above. Okay, ultimately trap of 2 is looking for an area, so we do need to calculate the areas of our 2 trapezoids. Rob? Yeah, they're both slightly above the curve. Yeah, and there's some characteristic of this particular curve that makes it so the trapezoids are always above, and you'll answer that in the activity. Okay, so how do you find the area of a trapezoid? All right, so you could cut your trapezoid into a rectangle with a triangle on it, and that's okay. But the trapezoid area formula is not so bad, and you probably saw it way back when in a geometry class. So here it is. Let's use the fancy trapezoid formula. It's half the height times the sum of the bases. You can see in the diagram of the trapezoid, the bases are the parallel ones, so they are the vertical sides in this case. So let's go ahead and label our diagram. What is the height for each of our trapezoids? If they're both 1s, our heights are horizontal in this picture. So 1 is the height for both of them. And let's go ahead and find the bases. How tall, how long is this first base here? It's 3, and the middle one is 12, and the last one, 27, which are exactly the numbers that we had before, and even if we didn't have them before, we know how to find them, right? You plug 1, 2, and 3 into that function. Those are your 3 bases. And then we just use our fancy formula here. So let's do the area of the first guy. So the formula over here says half of the height times the sum of the bases. So half of 1 times 3 plus 12. So is that 15 over 2? That's it. Go ahead and take a moment to find the area of that second trapezoid. And check in with each other. Any questions on 39 over 2? Okay, so then the last thing, again, finding trap of 2 means adding the areas of all the trapezoids. In this case, there's only 2 of them. So we add these guys up. And what do we get? So we'll just write it here. Trap of 2 equals 15 over 2 plus 39 over 2. What is that? 54 over 2? Just 27. Andy, a little louder.
That looks eerily similar to if we took the right-left sums and then averaged them.
Yeah, look at, all right, so everybody's down here with the 27, right? That's the 2 trapezoids added up. Ben had suggested, hey, before we do trapezoids, why don't we average? At least that would be better than either our 15 or our 39. But if you average 15 and 39, what do you get? You do get 27. All right, so now we have on the next page, this is part of the activities, but you guys ruined it, so we'll just look at it here. All right, so we'll call it the Ben-Andy theorem right here, is that if you just average the left and right, meaning add them up and divide by 2, you get the trapezoid approximation. Note that these are ends here. This is not specifically only because we were doing 2 rectangles or 2 trapezoids. It's all the time. The 2 in the bottom isn't that 2 trapezoids, right? It's just how you average 2 numbers. Okay, so I suppose we've just done this part here, but we'll write it out and then you'll continue the activity. If you wanted to use this formula, we would say, what was the left approximation in this case? 15 plus the right approximation, 39, and then divide by 2 because that's how we average. And lo and behold, the same 27 we had before. Okay, so you're going to continue the activity here in number 2. Before you do, one quick announcement. Part of your homework assignment, like if you just go, you don't need to go find it, but a few pages later in the packet where you find the normal homework assignment, it references doing 2 problems in the 5th edition. Now, most of you have the 6th edition, and so it says, hey, you'll find the 5th edition in the Math Studio. So Caitlin was generous enough to actually just type out those 2 problems. So maybe staple this to the homework page or something, but these are the 2 problems. You don't need to go scrounging around to find the 5th edition. It's right here. All right, so everybody have a copy of that from your table. Okay, raise a flag if I can help.